Hello everyone, and welcome back to Total Organic Chemistry. This video, we will be looking at the E2 mechanism for elimination. So the questions that you should be able to answer by the end of this video are, what is an E2 reaction and how does it work? So what is the mechanism? And also, which conformational isomers of organic molecules undergo E2 reactions in general? If you need any additional review or you would like to brush up on your E1 reactions or elimination reactions or also nucleophilic substitutions in general, please go ahead and subscribe and also take a look at my previous videos on those topics. So without further ado, let's get into it. Let's draw this pretty simple elimination reaction here where we have propyl bromide. I'll draw that here. And let's say we'll treat it with this potassium tert-butoxide. So remember, the tert-butoxide anion is a strong base, and it's also pretty sterically hindered. And we find out from this reaction, we actually get propene. So this bromine will come off, and we end up with forming an alkene here. So for an E1 reaction, this would mean that we would have to form the propyl carbocation, which would be relatively high in energy because it's that primary carbocation. And remember, primary carbocations are not stable, so this reaction would probably not follow E1 kinetics. So what we find out is that this is actually an E2 mechanism, which stands for bimolecular elimination rather than unimolecular elimination like E1. And bimolecular eliminations occur quite commonly with strong bases and especially sterically hindered bases. So bases such as the T-butoxide anion, where it has that O-, so it's pretty strongly basic, and it also is very sterically hindered with all of those methyl groups. So what is the mechanism for this reaction? How does it actually occur? Well, we can draw out the propyl bromide again, and this time let's explicitly draw in the hydrogen adjacent to the leaving group. So on this adjacent carbon here. And what's going to happen is, instead of the E1 mechanism, where we lose the leaving group to begin with and form a carbocation, our T-butoxide anion, I draw that here, will actually come in and it will abstract this proton from the adjacent carbon to the leaving group. This bond to the hydrogen will actually swing over to make that double bond just like we had in the E1 reaction. And all in the same step, the bromine leaving group will come off of the substrate, forming this propene alkene product in the end. So what this means is that this reaction is concerted, much like an SN2 reaction that we talked about previously, where everything, all of the arrow pushing happens in one single step without any intermediates. And also remember that concerted reactions like this, so we have two molecules in the rate determining step, that's going to follow a second order rate law. So our rate of an E2 reaction will depend on both the concentration of the substrate, so the haloalkane, and also on the concentration of the base that we're using. Something else to take into account with E2 reactions is that the hydrogen that's coming off and the leaving group have to be what's called antiperiplanar. So that means they have to be anti to each other in that configuration in order to actually undergo the E2 reaction. So what do I mean? Let's draw the same propyl bromide molecule that we had in the previous page. And let's draw a projection of the stereochemistry. So I can draw that here, where on the right side we'll have the bromine leaving group kind of going up with the two hydrogens on that carbon as well. And then on the left-hand carbon, we'll have, say, the methyl group can be coming out at us, and then we'll have also two hydrogens, one pointing down and one going into the page. I will also draw a Newman projection of this molecule. So I'm going to draw this little eyeball here, kind of looking from the left towards the right-hand carbon. And if you need any review on what Newman projections are or how to interpret them, please take a look at my previous video on that topic as well. So let's draw this Newman projection here. We have the front carbon, where we have these three substituents, so the hydrogen pointing down, hydrogen pointing sort of left and up, and then the methyl group going to the right and up. And then for the rear carbon, we have again the bromine pointing upwards, and then the two hydrogens are pointing to each side, left and right. So remember that anti means that they're on opposite sides. So we have the hydrogen here, anti to the bromine leaving group. And that is going to be the hydrogen that is pulled off in the E2 mechanism. So why is that the case? Well, this actually allows for the p orbitals to line up in the best way possible in the transition state in order to form that pi bond for the double bond in our alkene product. So remember that alkenes have a double bond which consists of a sigma bond between the carbons and also a pi bond where those p orbitals overlap. And so the p orbitals can overlap much better when the hydrogen and the leaving group are antiperiplanar to each other. Let's take a look at some consequences of that requirement for E2 reactions. So we'll start with two cyclohexanes, and this first one will have a tert-butyl group here, as well as a bromine, and let's say they'll be arranged cis, so both substituents will be coming out of the page towards us here. If we treat this molecule with NaOH, so a pretty strong base, and heat it up a little bit, we're going to end up with the elimination product here. So the bromine leaving group will come off, and will form an alkene. And so this reaction will actually happen pretty quickly, pretty readily. However, if we draw a different isomer of this cyclohexane, say if we draw instead of the tert-butyl group going out of the page, let's say it's going into the page, so it's arranged trans to the bromine leaving group. If we expose that molecule to the same conditions, we will end up with the same product, but we find out that this reaction is much slower than the first reaction. So why is that the case? So it's a little hard to see with the cyclohexanes drawn this way, but let's take advantage of our chair representations and draw those substituents on that way. So I can draw this chair structure here for the first molecule, and because the tert-butyl group and the bromine are cis to each other, we know that they both have to be pointing up or pointing down, it's equivalent. And we also know that the tert-butyl group is going to be very sterically hindered, so it will prefer to be in the equatorial position. So let's put that in the equatorial position here. And then we know that the bromine has to be pointing up as well, because it's cis, so we'll put that in the axial position on this other carbon. And if you're confused on equatorial or axial substituents, or how to determine which is more stable, please take a look at my previous video on substituted cyclohexanes. So because this bromine is in the axial position, it has access to an antiperiplanar hydrogen. So this hydrogen on the adjacent carbon is pointing straight down in the axial position, so it is antiperiplanar to the bromine, and that is why this first reaction occurs very readily. It has access to that very stable conformation with antiperiplanar hydrogens to the bromine. Okay, so what about the second molecule with the trans substituents? Well, we can draw the same chair skeleton here. And again, we know that the tert-butyl group is going to almost always be in the equatorial position. So let's draw that again here. But this time the bromine is again trans to the tert-butyl group, so it will have to be pointing down in this case. So it will also be in the equatorial position. And if you can see what's coming, in the equatorial position, this bromine has no access to any antiperiplanar hydrogens. So none of the adjacent hydrogens are antiperiplanar. And in order to undergo an E2 reaction, this trans isomer of this cyclohexane would have to undergo ring flipping in order to get that bromine in the axial position, but that would also put the tert-butyl group in the axial position, which is very energetically unfavorable with all of those steric interactions. So this reaction in an E2 mechanism will be much slower than the cis substituted cyclohexane. Okay, I'd like to take a look at one more reaction before the end of this video. So let's draw another substituted cyclohexane. And this time we will have the bromine leaving group on this carbon, and it will be coming towards us. The methyl group here will be going into the page on the same carbon, and then we'll have another methyl group also going into the page on this adjacent carbon here. And we're going to treat this molecule with sodium methoxide. So again, a strong base, not super sterically hindered, but we do have a pretty sterically hindered substrate. Again, we have a tertiary haloalkane, so we know that this molecule will likely undergo an E2 reaction. And what are the products of this reaction going to be? So let's figure that out. We know that in order for an E2 reaction to happen, we have to be able to pull off a hydrogen from the carbon adjacent to the leaving group carbon. Okay, so which hydrogens can we pull off in this molecule? Well, we could imagine pulling off the hydrogen here. I will draw that in black, and then that would produce this product that I'll also draw in black with the double bond between these two carbons here. Another hydrogen we can pull off, I can mark that in blue, would be this hydrogen also on the ring, and that would give us the double bond on the other side, so in between these two carbons. And finally, we can pull off this red hydrogen here on the methyl group, so that would give us this red product here with the terminal alkene, so the alkene between what was the methyl group and the ring. Okay, so that's great. Will all of those products actually form? Well, let's take a look at the other consideration we talked about, and that is about antiperiplanar hydrogens. So which of these hydrogens are actually able to be antiperiplanar to the bromine leaving group? Well, let's figure that out by drawing a chair conformation again. It's very useful. So we can draw the skeleton, and then we'll have let's imagine the bromine going up, so in the axial position. Then the methyl group on that same carbon will be pointing down, so in the equatorial position. And then the adjacent methyl group also has to be pointing down because it is cis to the other methyl group. So it will be in the axial position, which means that we have the hydrogen on that carbon in the equatorial position. So this hydrogen here is not antiperiplanar to the bromine leaving group, which means that we can actually not form this blue product here, because this molecule has no access to an antiperiplanar hydrogen in order to form that double bond. The other two products could feasibly form because they have those antiperiplanar hydrogens, so the black hydrogen and also the red hydrogen could be in conformations that allow them to undergo that E2 reaction. So whenever you're working with E2 reactions, it's very important to pay special attention to the conformations of your molecule and to whether those hydrogens can actually participate in an E2 reaction or not, even if the conditions are right. And that concludes my video on E2 reactions and the mechanism by which they occur. Thank you again for watching Total Organic Chemistry, and please subscribe to my channel and like this video if you learned anything. And also please consider donating to my Patreon page. I will link that in the description, and that really helps me to continue creating these videos for you and providing content to help you learn.